So a very good day to all of our attendees. My name is Vidish, and on behalf of Midas IT, I'd like to extend a very warm welcome to each and every one of you for attending today's web session on column shortening analysis considering creep and shrinkage. So on your screens, you can see the contents of today's presentation. I'll be talking first a little bit about Midas Gen, and then we'll dive in right to the crux of our presentation, where I'll introduce column shortening. I'll show you some of our project applications that wherein column shortening analysis has been done considering Midas Gen. Then I'll explain the procedure for construction stage analysis, which is very important when we need to consider column shortening. And finally, we'll come to the demonstration of it. So before moving further, for those of you who are attending the web session for the first time, or for those of you who are not yet familiar with the software GoToWebinar, this particular slide gives you some pointers. You can hide the dialog box by clicking on the red arrow, and if at any point you have any questions, you can just type your questions into the questions box, and once the presentation is over, I will take some time to address each and every one of your queries. Also, for your information, this webinar session is being recorded, and once the webinar is over, a download link for the recording will be sent to each and every one of our attendees so that you can download the recording and view it later as per your convenience as well. So let's get right into it now. First, let me talk a little bit about what Midas Gen is. Well, Midas Gen is a finite element analysis software that is catered to building engineers, but is also a general purpose tool. So it has very advanced capabilities, particularly it has capabilities regarding seismic functionalities. So you can conduct anything from the normal static seismic analysis to the highly advanced nonlinear time history analysis. It also supports pushover and capacity design. We have included comprehensive design support within Midas Gen, so it supports the design codes of nearly all major codes used in the world today. It has specific high-rise related functionalities, so 3D column shortening is available. We have a building model generation wizard that allows for very quick generation of a building model. There is automatic mass conversion, so for converting loads to masses when you're conducting seismic or eigenvalue analyses. And we have material stiffness changes for crack sections. So the crack section the crack section stiffness can also be taken into account. So let me now give you a short introduction to column shortening. Well, first of all, column shortening is a phenomenon which is basically the reduction in length of a column in a particular structure under the acting permanent loads. So basically a column in any building, a column is subjected to gravity loads, to live loads, to all kinds of loadings. And under these loads, the column tends to reduce or shorten in length over a period of time. This particular phenomenon is referred to as column shortening, and the effects of column shortening can be boiled down to two basic categories. We have non-structural effects, which include deformation in the pipes, elevator rails, cladding, etc., and cracks in the partitioning of walls. And there are structural effects. So the structural effects include the distortion in slabs or beams due to differential movements and gravity load redistribution. So the structural effects happen particularly in case of where buildings or where the structure plan is asymmetrical. So this particular slide shows the column shortening effects in a bit more detail. So here you can see from the images the deformation and breakage of facades, windows, and parapet walls. the reverse inclination of drainage pipe systems, deformation of the vertical piping system, and even deformation and breakage of the internal partitions. Now, so to analyze the effect of column shortening, construction stage analysis is very important, particularly more so in case we want to consider the differential column shortening. So this slide before your screens, it shows you the 4 major causes of column shortening. So you have the elastic stresses that arise from gravity loads, creep, which is again caused by the permanent loads or the gravity loads, drying shrinkage, and temperature variations in the exposed columns. The table at the bottom of the slide shows a comparison between the shortenings of an 80-story column. So as you can see, for steel buildings, we will not have creep or shrinkage, therefore only elastic shortening need be considered. Whereas for concrete sections, for concrete buildings, we'll have elastic shortening as well as shortening from creep and shrinkage, which together is sometimes referred to as inelastic column shortening. So overall, as you can see, the total shortening is actually quite comparable, 19.6 centimeters in the steel building and 16.8 centimeters in the concrete building. So in basically the concrete column, shortening due to shrinkage and creep comprise around 30 to 40% for the creep and 20 to 30% for the shrinkage respectively. Now let me go into a bit more detail about why construction stage analysis is so important. I've already explained that for considering the differential column shortening, one needs to consider the construction stage analysis. But this is only part of the reason. The other part of the reason is that the dead load that acts on a building is in real life a sequential load. So we have our live load and wind load and the earthquake loads. Now these generally we consider to act on the completed structure. The dead load, however, depends on the construction sequence. So at any particular time t, whatever part of the building model is complete, the dead load will only act upon that part. And because of this, the response of the structure to the dead load may be different from what we normally would get if we did not consider the construction stage analysis. To further my point, let me show you this particular slide. So on your screens, you can see this is the conventional analysis of a 2-story structure that we would do normally if we did not consider construction stage analysis. So we would definitely apply the dead load on the two slab portions directly, and this is equivalent to applying the dead load first on the bottom slab and then applying the dead load on the upper story. However, in the construction stage analysis, this is the way the load is applied both in CS analysis as well as in real life. Now here you can very easily see what the difference would be. Because in the earlier image for this particular half, we had the 2-story frame structure for both cases. And this means that for the same loading, there would be greater redistribution in the conventional analysis case than there would be in the CS analysis case. So because the CS analysis case has lesser redistribution, there is more localization of the dead load forces, and therefore we have slightly different bending moments or responses from CS analysis than if we consider the conventional analysis. Finally, this particular graph shows a comparison between an 80-story building where the analysis has been done considering with and without the sequential loading analysis. So here, as you can see, there is a very significant difference as the number of stories goes up. So that at the 40th story, here you can see that there is a very significant difference. The blue line represents the conventional analysis, whereas the pink line represents the construction stage total difference. So here there is about 40% difference in the negative moment zones. Now, coming back to column shortening analysis. So in column shortening, there are two major ways in which the column shortening can deform the structure. We can have a vertical deformation, which is a direct result of the vertical shortening of the column. It can also result from settlement, or it can come from construction errors. We have horizontal deformation, which is a result of differential shortening. It can also result from settlement or uneven loading due to construction method or an asymmetric floor plan, or again construction errors can also cause it. So basically the column shortening in any particular concrete structure would be the elastic deformation added to the inelastic deformation. And as a general rule of thumb, the inelastic shortening can be considered to vary between 1 to 3 times the elastic shortening. Expanding a little bit more on these rules of thumb that I had just explained. So for steel columns or for steel buildings in general, the only elastic shortening is to be considered, and the shortening usually varies between 1.5 to 2 millimeter per floor. And for concrete columns, you can consider that the elastic shortening varies about between 0.5 to 0.8 millimeter per floor. Creep can be extended to be about 1 to 2 times the elastic shortening, while shrinkage is again about 0.2 to 0.5 millimeters per floor. So overall, the two effects, that is the effect in the steel column and in the concrete column, are quite similar. The only difference is that they happen at different times. So in the steel building, the effect is rather immediate because of the elastic nature of the shortening, whereas in concrete, the effect may take a few years to develop. Now, this slide shows you the shortening related to the installation. So when we are, in order to prevent the differential column shortening, we need to compensate for the amount of differential shortening that will come during construction. So this compensation has to be calculated using the by calculating the amount of shortening that will happen. So we have basically two types of shortenings here. We have pre-slab installation shortening, that is shortening of supports that happens at the time of the slab installation, and then post-slab installation shortening, that is basically once the slab is installed and the load from the slab is also acting on the supports, there will be an additional shortening phenomena occurring after that. So in this picture, the line number 2 in the image that you see on the screen, the line number 2 is the design level, the level at which we want our slab to be finally. So the engineer needs to consider the compensation level required to make the slab follow the line number 2 after a certain period. So line number 3 basically represents pre-slab installation shortening, and line number 4 is post-slab installation shortening. So normally the compensation follows somewhere around say line number 1. So what this basically means is that at the time of construction, or at the time of the pouring of the slab concrete over the support formwork, we level the formwork in an inclined position such that once the shortening occurs and the formwork is removed, the slab orientation will be along line 2. And additionally, for there are, of course, for different kinds of buildings, there would be different levels of compensation. So for reinforced concrete structures, pre-slab installation shortening does not have much importance because of the reduced level of elastic shortening. Compensation is usually done by additionally compensation is usually done by leveling the forms. So post slab installation shortenings and the subsequent effects from dead load, that is from creep and shrinkage, these are of much more importance in RC structures. In steel structures, however, the columns are fabricated to an exact length, and there are attachments to support the slabs. So pre-slab shortenings, they need to be known, and compensation for the summation of pre-installation and post-installation shortenings, this needs to be calculated. Now, the overall procedure for applying or for calculating the column shortening is basically, first of all, we do a pre-analysis where we get an initial estimation of the amount of shortening that will happen at each story level using the initial material and section properties and the applied loadings along with the construction schedule. So once the preliminary design is done, during construction, once at the construction of each story, we need to keep on updating the analysis results with the field data. So the main analysis is done by updating material properties from experiments and then construction sequence considering the field conditions as well. So in the field, continuously the measurements need to be taken using the strain gauge or other related instruments. So first, third, basically a large number of reanalyses have to be made by taking into account the field data as well, until finally at the final report we get the actual value of shortening, which is comparable both from the tests and from the model analysis. So this slide will basically show you a breakdown of the contribution to shortening by the different variables. So material properties have a 30 to 40% contribution to the overall shortening. The environmental condition, that is the temperature, relative humidity, these also provide a 30 to 40% contribution. And the construction schedule and field conditions have a 15 to 25% contribution in the total shortening value. So pre-analysis is performed based on several assumptions of construction schedule, material properties, and environmental conditions. So because the pre-analysis considers the best case construction schedule, so obviously in the field the construction schedule may sometimes need to be changed depending on the site conditions or depending on certain other unpredictable variables. So that is another reason why the reanalysis needs to be done again and again to account for the variability of the construction methods. And this particular slide shows the basic idea of installation of the slab faces or the slab columns. So as you can see, the slabs themselves are placed at are cast in an inclined position, so that once the shortening occurs, the overall deformation would be equivalent to the height of correction in the image that you can see, and so that ultimately the slab gets placed in the horizontal level that we desire it to be in. Now let me very briefly talk about two other factors that will affect tall building design. The first of these is wind response. So the crosswind response in this graph that you can see on your screens, where the crosswind response is plotted against the wind velocity. So here, as you can see, a kink in the graph is pointed out as vortex shedding. So vortex shedding is basically a phenomenon that very adversely affects tall buildings, particularly supertall structures in high wind areas. So the vortex shedding creates a sort of lateral movement of the building perpendicular to the direction of the wind velocity. And this lateral movement, of course, would adversely affect the overall building performance and needs to be investigated and stabilized against. So in the formula that you see on the screens here, N is the shedding frequency, B is the building width, and S is the Strohal number. So these are normal terminologies that are used in fluid mechanics. And additionally, the wind effect in tall buildings is almost always investigated using wind tunnel testing. And this not only helps us in gauging the wind effect on the structure, but also helps us find the optimal cross-section for different floors. So, for example, when we go for a building design, we normally when we do a wind tunnel response, we normally do it for several different types of cross-section for the building. So starting with, let's say, a cylindrical or a rectangular cross-section, then a slightly more tapered off cross-section or things like that, basically to observe the effect of those different effects and finally arrive at the most optimal cross-section with respect to wind response. The second factor I will briefly discuss with you is the seismic response. So obviously in areas of high seismicity, appropriate measures need to be taken to ensure the structural stability of a particular building. So nominally so usually the systems that we normally use are systems like tune mass dampers, base isolators, lateral force resisting core walls. So each of these structures are very commonly used in high seismic areas. For example, one of the fifth largest or the fifth tallest building currently in the world, the Taipei 101 Tower in Taiwan, it utilizes a tune mass damper, and you can see the image, the image on the farthest right on your screens right now. That is the image of the tune mass damper from the Taipei 101, which has been installed somewhere between the 87th and the 91st floors on this particular building at a height of about 390 meters. The other two images here represent the core walls, the core wall philosophy. So as you can see here, we have an RC core wall, which is very stiff and is used primarily to resist the lateral forces. And we also have seismic base isolators. So these are, for example, lead rubber bearing isolators, which can be installed at the base of a building to seismically isolate the top half of the structure from the rest of the foundation. Now let me show you some project applications of Midas Gen, wherein column shortening analysis was done. So the first application that I would like to show you is the Burj Khalifa, the tallest building in the world, with a total height of about 800 meters or 705 if we do not consider the spire. It has 160 floors, and the general contractor, Samsung, utilized our product Midas Gen for conducting construction stage analysis and column shortening analysis as well. So here is our software, and here, as you can see, is the model of the Burj Khalifa. So let me show you how the different stages were created and how the model was visualized on Midas Gen. So at the first stage, we only have the foundation, the support, along with the support conditions, and the core walls that are now being raised. So here, as you can see, the walls are being raised along the core first, and once that is done, the side structures are now being raised. So in this fashion, the structure keeps on going. The structure is modeled continuously throughout the different stages until finally we have reached the top, the final stage wherein the structure is finally complete. The second project application is the SKS Trenu Tower in Seoul, in South Korea. So it has about 36 floors, and the lateral load resisting system is an RC core wall plus a steel and RC composite frame system. And let me show you this particular model as well. So this is the model of the SKS Trenu Tower. So its staging was slightly more interesting in that it used the top-down method of construction. So first the basement wall for the construction was created, and finally, once the basement wall was done, then we started creating the top half of the structure, and from there it used the top-down method. So as you can see, this is the top-down method of construction. Until finally the complete building is created again. Once the base is complete, the frame on top is now started, and at the end we have the final model. So this building utilized composite sections as well, and for composite section, Midas Gen can also consider the sequence of composite columns. So for composite columns, generally the steel section is installed before the concrete is cast. So Midas Gen can also consider that. And finally, we have the Kiang Nam Hanoi Landmark Tower in Vietnam. So this basically has three different towers. The first is a 70-story main tower, and two supporting towers of 49 stories each. So let me show you this particular tower. So here is the 70-story tower. And once again, the same sort of construction methodology was used. We start off at the base, and we simply work our way up. Okay, now let me come on to explain the basic procedure of construction stage analysis in our software Midas Gen. So this particular slide shows you the flowchart for using the construction stage analysis feature in our software Midas Gen. So first of all, we define our materials. We assign the elements, boundaries, and load groups. We define the time-dependent material properties for creep and shrinkage, and also for compressive strength variation. And then we enter the construction stage analysis data and perform an analysis. Then finally, we go on to check the results and check the column shortening as well. So with regard to the time-dependent material properties, so different countries utilize different codes for the creep, shrinkage, and compressive strength variation. So in our software Midas Gen, we have support for nearly all the major time-dependent codes. So we have Eurocode, ACI, CBFIP, India, and very recently the Australian code has also been implemented for creep, shrinkage, and compressive strength variation. So the AS3600 is also available. And for construction stage analysis data, Midas has options where we can specify the duration of each stage and choose which elements will be enabled or which elements will be activated during a particular stage. So if there is no change in the element, instead of adding a new stage, we can use an additional step to reduce the total number of stages that we have to go through. So we can do an additional step in the same stage and check the results for that. And finally, we have options for the different kinds of stages. So when in the results we have a base stage, which is in the pre-processing mode, which is the stage for defining all the construction stages and the data. The construction stage itself, where you can check what you have defined, and the post-construction stage, which is a stage that comes at the post-analysis or the post-processing mode, where you can check for the final results. So as you can see, this is the way that results can be viewed. So you can create multiple windows as well within Midas Gen itself. And you can get analysis results for each construction stage, and absolute minimum or maximum results of an envelope can also be checked. And finally, for column shortening results, Midas provides very detailed column shortening graphs. So for the different facets of creep, shrinkage, and the elastic shortening as well. So we have basically two kinds of result parameters for each and every one of these phenomena. So post-slab installation shortening and pre-slab installation shortening. So both of these can be seen individually. Let me now very briefly discuss some useful features that Midas has for construction stage analysis that set it apart from other softwares in the market. So we have a building model generation wizard specifically for the construction stages. So this allows for very quick generation of different construction stages. So you may find it more convenient to just go for an automatic generation. However, if you want to manually enter the construction schedule, even that can be done using the Excel type input window that is available within Midas Gen. So as previously mentioned, that Midas Gen has support for construction stage analysis for composite sections. So once again, generally for composite sections, if you have a concrete encased steel column, the steel column is cast first, and the concrete is then later poured around it at a later stage. So Midas Gen can also consider this difference and this variability in the stiffness of the section over different time periods. And also we can consider the creep and shrinkage effect within the composite sections as well. Furthermore, you can change the material stiffness for considering the crack section properties. So for example, for seismic loadings, generally all codes specify that the section's properties should be considered as cracked section rather than uncracked section. So for this, you can modify the section properties for individual sections or for a group of sections as well, all at once. And of course, we also have support for soil structure interaction. So you can consider preliminary soil structure interaction in our software Midas Gen by using the different types of spring conditions that are provided. So here we have point spring supports, wherein we have linear compression tension only or multilinear type. We have surface spring supports, which is basically using the Winkler spring theory for distributed spring type, and springs can be generally activated or deactivated under construction stage using the boundary groups. So if at a particular time, let's say you're creating a temporary support condition, for example, if you are creating temporary supports and at a particular moment you are removing these supports, so even that can be modeled within Midas Gen. And finally, coming on to tenon losses. So Midas Gen also provides a tenon loss graph. So you can check the losses within the tenons in an interactive form. So at this point, let me switch over to a particular model and show you all of these features that I have just mentioned right now. I'll just close the files that I do not need. So this is a particular model of a building that I will be discussing with briefly right now. So here in this particular building, as you can see, we have tenant profiles. So we have tenants installed in this model at the transfer girder locations. And to deal with tenants, you can simply go for first define the tenant property. So here you have 3 different types of tenants available to you. Internal, you can have a pre or post tensioning, and you can even have external tenant types. And you can consider your tenant as bonded or unbonded. So once you have defined your tenant property, later on you can go and define your tenant profile. So the tenant profile, if you have it in Excel coordinates on your Excel sheet, you can simply copy paste those coordinates here in Midas Gen, and the tenant profile will be created accordingly. And once the tenant profile is done, you can go ahead and input the pre-stress loadings. So here we have the pre-stress load options. So from here you can input the pre-stress beam loads for your particular model. Now let me show you some of the result features. So under beam diagrams, so here let me show you the pre-stress results. So these are the different pre-stress results for this particular model, and we can even see the same results at different stages. So for example, at CS8, I can check the different results. I can check separately for creep and shrinkage. So I get separate results for creep, I get separate results for shrinkage, and I can separately see the primary and secondary effects of tendons. So this is the tendon primary effect, and this is the secondary effect of the tendons. Furthermore, you can see a tendon time dependent loss graph. So for example, if I choose this kind of a let's say tendon 4, I can vary that tendon over time and see how the force in the tendon is varying as a function of time. And I can save this graph as an image. I can save it as a text as well. Okay. And as for the other options, so for example, if you want to check the section stiffness scale factor, so you can directly modify the stiffness of a group of sections at once, or you can modify the section stiffnesses individually. So from here you can modify the moments of inertia, the total area, the weight of the section, and so on and so forth. Let me now go over to the demonstration half. So this is the model that we will be dealing with today, a simple 12-story structure. And this is the structure in plan and elevation. These are the different section sizes and the different material properties. So the girder will be 240 kg per centimeter square. That is its FCK. Similarly for column, and for the wall we have 28 MPa. Let me discuss with you a little bit about the construction schedule. that I will be showing you in this model. So we have 3 levels of shoring, and the construction cycle time here will be 7 days. So for the first day, we have just the formwork installation. On the third day, we have the concrete casting, that is, the concrete is poured into the formwork. Then on the 8th day, the second story formwork is installed, and on the 10th day, the second story formwork has concrete poured into it. Okay, so up until the 10th day, we are still in the formwork zone. We have not removed any of the formwork yet. So at every, as you can see, at every 8th, we have at every 3rd day, the formwork is being installed. And here we have on the 15th day, the 3rd story formwork is installed, and on the 17th day, the concrete is cast on the 3rd story, and the 1st story formwork is removed on the 22nd day. So on the 22nd day, the concrete slab on the 1st story is only 19 days old. So it's 19 days old because we started the pouring on the 3rd day of construction. So this is the way that the construction schedule has to be kept in mind. So in Midas, we do not deal with the construction stage duration, but rather we deal more with the age of concrete. That is there at the time of activation of the model. So on the 22nd day, the age of concrete, first activated concrete, is 19 days. Then on the 24th day, we have the 4th story concrete casting. And on the 29th day, again, the 2nd story formwork is removed, wherein again the age of the concrete is still 19 days. So each stage duration basically here is 2 days, but in between the activation of different concrete days, we have 7 days as the stage duration. So between the activation of the first concrete slab and the second concrete slab, there is a 7-day interval. So each stage duration now is 7 days. So this is the way in which the construction schedule, the field construction schedule, is translated to the software construction schedule. So as you can see, at the time of formwork removal, that is the time that we consider as day 1 for the model, for the structural model in the software. And as soon as the formwork is removed, the load is acting on the model, and we can then go on to analyze that particular part of the model. So in a similar fashion, the entire construction schedule is translated until finally you will see at date 92, we have here the superimposed dead loads that have become activated. So superimposed dead loads can include the finishings, the additional loadings from parapet or partitions. So basically all of these things that constitute any additional dead load acting on a particular story. So the superimposed dead load is activated on 3 stories at once, and the start date is 71. And it is activated 3 stories at a time until finally it reaches the 12th floor. And finally, the live load is activated on the last day, that is the 112th day in the program. So now let me shift over to a model. So this is the same model whose plan and elevation you saw in the presentation slide. And we'll be working on this model. So first of all, let me go ahead and create the material and section properties for creep and shrinkage. So under properties, we have time-dependent material properties. So here I'll add different properties for the beam, slab, and for the beam, the column, and for the walls. So for the beam, we have 24 MPa. The notational size I will auto calculate for the different sections. So here I'm just entering it as 1 meter. So with that, you can directly check once you have entered the data how the creep function is varying. Just click apply. Similarly, we'll do the same for column. Here it will be 28. And finally, for our walls. So it will be the same as the column. So now we have 3 different codes, and here the code that I have selected is CBFIP, but you can also select any other code as per your requirement. So we have different codes supported. For example, the European code is there, ACI, PCA, the AS, the Australian codes, as well as the Indian and the Russian codes are supported. Up next, we will apply the same properties for time-dependent material variation. So the variability of compressive strength can also be considered. So again, same thing for beam. I'll consider it as CBFIP. And under CBFIP, I have to add 8 MPa to the characteristic compressive strength. So here it will be 32 for the beam. I click on redraw graph, and this shows me the variability. Similarly for column, it's 36, and I can add the same thing for wall. Now finally, I need to assign the time-dependent property to the different material properties. So there's I use the time-dependent material link. So for the girder, I use the beam property. For the column, I assign it the column time-dependent properties, and for the wall, I assign them the wall property. So in this fashion, the time-dependent properties have now been assigned. And finally, you will remember that I had mentioned that the notational size I have entered randomly as 1 meter. So I will need to change that. So I can directly enter, choose the code. So for example, for CBFIP, I have the option to auto calculate the notational size of the member. So I can just select the elements, and automatically Midas will calculate the notational size of these members. So normally in your building, if especially in a very tall structure, you have different sections at different story heights. So at the top story, you will have a slightly thinner section, whereas at the bottom stories, you will have a thicker and larger sections for your particular columns or beams. So if because of these different sections at different story heights, it becomes a very difficult affair to manually calculate the notational size of each and every section. And this is where the notational size option, the auto calculation option, is very useful. Okay. So once we've done that, now let me go over and let me show you the construction stage analysis wizard. So we have this construction stage wizard. Sorry. And yeah, so this is the dialog box, or this is the interface of the wizard. So here you can either manually add the stages one by one, or what you can do is we can go for an automatic generation. So under automatic generation, First of all, I'll create the case for my static dead loads. So the story increment, so the dead load will increase one will go by one increment, that is the dead load will increase one by one at each and every story. The stage duration here is 7 days. So as I had mentioned before, that the time difference between the activation of the concrete or the removal of formwork, as I should say, between two different floors is 7 days. And the member age, so each member is 19 days old at the time of activation. Then we consider the application of the superimposed dead loads. So the dead load from the SIDL is being activated 3 stories at once. The starting age is 71 and the day increment, so it is being incremented at 3 days. Similarly, for superimposed dead load 2, we have, I'll enter the variability of the live load. So story increment here, I will just put it as 12 because the live load is being activated all at once. And starting day is 112. And since the live load is being activated at the all at once, we don't need to enter there will be no further day increment for it. I'm only entering 1 because Midas Gen will not take a 0 value for day increment. So you can enter any number except 0 here. And once you click OK, you will see all the data has been entered for your building. And you can go ahead and click OK now. And in the worktree, we can see that the different construction stages have automatically been created. And from the stage view, I can even check how these different stages have been created. So for example, CS1, this is the first stage, CS2, CS3, and so on. So in this way, you can very quickly create a construction stage model. And furthermore, if you want to modify a particular stage, so here I just clicked on the construction stage but option over here. If you want to modify a particular stage, for example, if you know that a particular stage will take slightly more than 19 days, so you can just go to modify here and you can easily modify the stage duration. So here, if the age of particular member is slightly different, or if the stage duration is more than 7 days, so you can directly change that. You can change the boundary conditions and the loading conditions. You can choose what group you want to activate or deactivate as well. So with that, let me change to a pre-analyzed model. So this is the same model that has already been analyzed. And here, let me show you some of the results. So for example, the combination results that you can check. So again, these are the same, the bending moment diagrams. And if you change through the different stages, you can directly get the results for dead load, live load, creep, shrinkage, and also summation load case. That is the summation of all the construction stage loadings. Okay. So for example, this is the variability of the creep throughout the different stages. So you can get a measure of how the creep is affecting. So this is the secondary effect of creep. And through the different stages, you can directly see how the creep force is changing. Now, finally, let me come over to the column shortening graph for the construction stage. So if you want to create a particular graph, let's say, for example, let me go into the top view, the plan view here, and I want to check a particular column for column shortening. So let me give it a name. Let's say I name it as test, and I'm going to choose the column that is present at the origin level. Now the result text output, as I've already explained here, so you can get different result outputs. So for example, you can get the elastic shortening before the slab installation, elastic shortening subsequent to slab installation, or the elastic shortening that is a total directly including both the effects. So let me select all, and you can choose, for example, here you have the different stages, and so let me choose the creep total, the elastic total, the shrinkage total, and let me now go ahead and choose, let's say, 3 years later. That is, I'm looking at a time 3 years into the future. So how much will the shortening be for this particular column? So here you can see the overall value of the column shortening as a function of time. So for example, example here, you can see the elastic shortening is in green. The red line shows the creep shortening, and the blue line shows the shortening due to shrinkage. So in this way, you can easily get the graphs, and you can save these graphs even as an Excel sheet. So the graph itself can be converted to an Excel sheet and can be saved as Excel. So with that, I would like to bring today's web session to a close. Thank you once again for having taken the time from your busy schedules to attend this web session. If you have any questions or any queries, I would like to address them now.